Imagine waking up inside a glass dome on the surface of the moon. Through the curved walls you can see the ink-black sky, the craters stretching out in every direction, and the Earth hanging silently in the distance like a blue marble. Now imagine that the dome you are living in was not shipped from Earth. It was not assembled from prefabricated parts, delivered by rocket. It was built right there, on the spot, using nothing but the dust beneath your feet. That is not science fiction. That is the plan that NASA is actively funding, developing, and preparing to make real. And the technology at the heart of it is something that most people have never heard of. High-powered lasers melting lunar dust into glass-like ceramic structures, layer by layer on the surface of another world. No cement, no timber, no steel beams, just dust, laser energy, and a machine smart enough to turn one into the other autonomously, without a human hand anywhere near it. Let us start with the fundamental problem that makes building on the moon so extraordinarily difficult. Everything you take from Earth to the moon costs an almost unimaginable amount of money. Experts working with NASA on the Artemis program have estimated that every single additional kilogram of weight added to a space mission costs around $1 million to get off the ground and delivered to the lunar surface. $1 million per kilogram. To put that in perspective, a bag of standard building cement weighs around 25 kilograms. Bringing enough cement to construct even a basic small structure would cost hundreds of millions of dollars before you even begin mixing it. Bringing steel, timber, glass panels, wiring, plumbing fixtures, or any of the other materials that go into a modern habitat would push the cost into territory that makes the entire concept financially impossible. This is why NASA's approach to building on the moon is built around one core principle. You cannot bring the materials with you. You have to use what is already there. Scientists call this concept In-Situ Resource Utilization, or ISRU. It is a straightforward idea with an extraordinarily complex execution. The moon already has material on its surface in enormous quantities. That material is called regolith. It is the layer of fine, powdery soil that covers the entire lunar surface to depths of up to 70 meters in some areas. It has been there for billions of years, produced by the constant bombardment of meteorites smashing into the moon and pulverizing its rocky crust into dust. And it turns out that this ancient, abrasive powder holds the answer to building humanity's first home on another world. Lunar regolith is not like the soil in your garden. It is nothing like it. Each particle is jagged and angular, because without an atmosphere or water on the moon, there's no wind or rain to erode the edges smooth. The particles are so sharp and so fine that they behave like microscopic shards of glass when disturbed. During the Apollo missions, astronauts found that moon dust clung to everything. It got into visors, jammed equipment joints, coated spacesuits, and caused persistent problems throughout every mission. Katie Kuby, a materials scientist at Icon Technology, a Texas-based construction company working directly with NASA, has described each particle as jagged and angular, and explained that when a rocket lands directly on the moon's surface, the dust it kicks up essentially sandblasts the entire surrounding area. But here is the extraordinary thing about this highly problematic material. When scientists at NASA's Marshall Space Flight Center in Huntsville, Alabama, began studying the tiny samples of real lunar regolith brought back from the Apollo missions, they discovered something remarkable. Under the right conditions, with the right amount of directed heat energy, lunar regolith melts, and when it solidifies, it transforms into a material that is hard, dense, and capable of withstanding temperatures approaching 1900 degrees Celsius. It can resist radiation. It can handle the brutal temperature swings of the lunar day and night cycle, where surface temperatures swing from over 100 degrees Celsius in sunlight to negative 170 degrees Celsius in shadow. In short, melted lunar regolith becomes one of the most practically useful construction materials imaginable for exactly the environment in which it exists. The moon hands humanity its own building blocks, already engineered by billions of years of exposure to the harshest environment in the solar system. The question was how to melt it, and that is where lasers enter the picture. A research team at The Ohio State University, led by graduate researcher C.J. Shu, published findings in early 2026 in the journal Acta Astronautica that represented a significant breakthrough. They used a technique called laser-directed energy deposition, or LDED. The process works by feeding powdered regolith directly into a laser or generated melt pool. The laser heats the material to its melting point in a highly focused, controlled way. As the molten material is deposited, it cools rapidly and solidifies into a new structure. Layer by layer, the machine builds upward, fusing each new layer to the one beneath it, creating a single cohesive object with no seams, no joins, and no weak points between separately manufactured sections. What the Ohio State team found when they analyzed the solidified material was striking. At high temperatures, the lunar regolith simulant they use transformed into a mix of mineral phases dominated by anorthite, with additional amounts of mullite and quartz. Mullite, in particular, is a ceramic compound renowned for its thermal stability and exceptional mechanical strength. It is used in high-temperature industrial applications on Earth precisely because it does not weaken under extreme heat. Finding it emerging naturally from the laser melting process of lunar regolith means the material produced is not just adequate for lunar construction. It is genuinely strong and durable by any engineering standard. The team also identified a critical finding about surfaces. When they attempted to print the melted regolith onto stainless steel, the material formed bead-like droplets that failed to bond properly. On glass, it fused at low power but cracked when heat increased. But on an alumina silicate ceramic base, the melted regolith adhered strongly and consistently. The researchers concluded that the chemical similarity between the base material and the printed regolith encouraged crystals to form across the interface, dramatically improving adhesion and structural integrity. For future lunar construction systems, this means the surface preparation and base material choice will be as critical to the final result as the printing process itself. But the Ohio State research represents just one branch of a much larger effort that NASA has been systematically building and funding for years. The centerpiece of that effort is a program called Project Olympus, developed by ICON, a construction technology company based in Austin, Texas. ICON already uses large-scale robotic three-dimensional printing on Earth to construct homes, and the company has been partnering with NASA since 2020 to adapt that technology for the lunar environment. In late 2022, NASA awarded ICON a contract worth $57.2 million under Phase 3 of its Small Business Innovation Research Program. The money was specifically designated to develop the Olympus Construction System, a multi-purpose robotic printing platform designed to use lunar and Martian regolith as its sole building material. The contract runs through 2028, and ICON has been working alongside NASA's Marshall Space Flight Center under a project called the Moon to Mars Planetary Autonomous Construction Technologies Initiative, known as SIM-MMPACT. The goal of MMPACT is straightforward: increase the technology readiness level of large-scale additive manufacturing to the point where it can reliably build infrastructure on the Moon and eventually Mars. ICON has also built what it calls the Moonbox, a massive lunar regolith testing chamber capable of holding more than 70 tons of their superior lunar highlands simulant material in a controlled environment. The chamber includes a 6-degree of freedom motion capture system, adjustable lighting, and stationary robotic arms. This is where ICON tests its Olympus system at scale, under conditions designed to replicate as closely as possible the actual environment it will face on the Moon. The vision for the deployed system is for it to be integrated into a rover that lands on the lunar surface and autonomously drives to its target construction site, where it begins printing without any human operator directing it in real time. Roads, landing pads, blast shields, and eventually habitats, all built from the dust the rover drives across. The Olympus system uses a process ICON calls laser vitreous multi-material transformation, or LVMT. The technique uses high-powered lasers to melt local surface materials and deposit them in controlled patterns, forming strong ceramic-like structures as they cool. The word vitreous refers to glass-like properties, and that is precisely what the material resembles when it solidifies. Hard, smooth, dense, and almost translucent in some conditions, it is not fragile like window glass. It has the structural properties of an industrial ceramic, which is an entirely different class of material, and it can be built into shapes that traditional manufacturing could never achieve on a planetary surface without a full factory operation. But even as Project Olympus represents the mainstream of NASA's lunar construction effort, an even more ambitious concept has appeared alongside it. In 2025, NASA's Innovative Advanced Concepts program, known as NIAC, selected a proposal from a company called Skyports for Phase 1 funding. The concept is called LUNGS, which stands for Lunar Glass Structure, and it represents a vision of lunar habitation that goes far beyond anything previously proposed in terms of scale and elegance. The LUNGS concept, led by Skyport's CEO Martin Bermudez, proposes melting the Moon's glass-rich regolith using a smart microwave furnace system rather than lasers. Microwaves are particularly well suited to the lunar environment because they couple directly with certain minerals in the regolith without requiring oxygen or combustion, neither of which are available on the Moon's surface. Once the regolith is molten, the LUNGS concept calls for blowing it into a monolithic spherical shell using inert gas pressure. In the near vacuum of the Moon and under its low gravity, the physics of this process work in an almost magical way. Bermudez has explained that the spherical shape forms automatically. Because at the required temperature, the molten material becomes an amorphous liquid, and when extruded from the furnace in low gravity, it naturally forms into a perfect sphere with remarkably uniform wall thickness. The resulting habitat could span up to 1,500 feet in diameter. The glass would be engineered to include polymer infusion that gives it a degree of self-repair capability, closing small fractures caused by micrometeorite impacts or the stress of moonquakes before they can propagate into larger cracks. The transparent material would allow natural sunlight through its walls, providing genuine daylight to the astronauts living inside. Researchers believe this could be vital for psychological well-being during long-duration lunar missions, where isolation and the absence of natural light cycles represent serious risks to crew health. Interior decks, lab spaces, greenhouses, and living quarters would be three-dimensional, printed on site from regolith-derived materials, minimizing the amount of mass that needs to be launched from Earth. Concepts under discussion include thermal zoning within the habitat, using temperature gradients within the structure to support condensation cycles that assist with plant growth and water recovery. The temporary gas lines used to inflate the molten glass sphere during construction could later be repurposed as entrance shafts and airlock conduits once the shell has cooled and solidified. NIAC. Phase 1 funding covers feasibility analysis and benchtop testing rather than full construction. But the fact that the concept passed NASA's selection process means it cleared a genuine scientific and engineering review. The agency does not fund fantasy. It funds concepts that the evidence suggests could actually work. The timeline for all of this is moving faster than most people realize. The Artemis program is actively progressing. A crewed lunar flyby was scheduled no earlier than April 2026 as Artemis 2. Artemis 3, the first Artemis landing, is targeted for 2027. The Olympus system is expected to accompany that mission, or a subsequent one, to demonstrate lunar surface construction, beginning with a landing pad, the most immediately critical piece of infrastructure for any sustained lunar presence. Without a solid landing pad, every rocket touchdown kicks up a sand-blasting wave of regolith that damages surrounding equipment and habitats. The landing pad is not a luxury. It is the foundation on which everything else depends. From there, the roadmap extends to blast shields, roads between facilities, structural berms for radiation protection, and eventually the habitats themselves. NASA and the European Space Agency are already planning the Lunar Gateway, the first space station to orbit the Moon as part of Artemis 4. The gateway will support surface operations and eventually assist with constructing habitable structures on the lunar surface. By 2030, the agencies expect to have the critical infrastructure in place to support a semi-permanent human lunar presence. By 2040, a sustained community living and working on the Moon is the stated goal. What is being built right now, in laboratories in Austin, in Huntsville, and in testing facilities across the country, is the foundation of that community. The laser systems, the ceramic materials, the autonomous rovers, the microwave furnaces, and the glass-blowing concepts are not distant dreams. They are active engineering programs, with real funding, real timelines, and real people working on them every single day. The Moon has been sitting up there for 4.5 billion years, covered in the same fine dust that an ancient universe deposited on its surface through an endless rain of impacts. For most of human history, we looked at it and saw a mystery. Then we walked on it. And now we are looking at that dust and seeing something completely different. We are seeing the walls, the floors, and the ceilings of the first homes humanity will ever build on another world. The glass moon is not a metaphor. It is a blueprint, and the lasers that will bring it to life are already being tested. But there is one more dimension to this story that deserves serious attention, because this is not only about the moon. Everything being developed and tested right now through Project Olympus, and the lungs concept is designed with a second destination in mind from the very beginning. That destination is Mars. The principles that make laser-melted regolith construction viable on the moon apply equally to Mars. Mars has its own regolith, its own mineral composition, its own resource base that is already sitting on the surface waiting to be used. ICON's Olympus system was always described as a multi-purpose construction system for both lunar and Martian resources. The M-Impact program at NASA's Marshall Space Flight Center has Mars in its name. The framework being built around using local materials to construct off-world infrastructure is explicitly a framework designed to take humanity as far as our solar system allows. This matters enormously for what comes after the moon. A human mission to Mars will take months each way. There's no resupply run. There's no emergency return within a reasonable time frame. Any sustained presence on Mars requires infrastructure that can be built, maintained, and expanded using only what Mars provides. The work happening in laboratories in Alabama and Texas right now is not just about building a landing pad near the lunar South Pole. It is about building the industrial and engineering knowledge base that will allow humans to inhabit an entirely alien world without depending on deliveries from a planet tens of millions of miles away. Northwestern University mineralogist Stephen Jacobson, who has received NASA funding to study the exact composition of lunar soil samples from the Apollo missions, has pointed out a challenge that is easy to overlook. No two scoops of lunar soil are identical. Different minerals within the regolith melt at different rates. The composition can vary dramatically across small distances. Any printing system deployed on the Moon or Mars needs to be smart enough to analyze each scoop of soil it receives, understand its specific mineral makeup, and adjust its laser parameters accordingly to produce consistent, reliable results. Jacobson and his team are building precisely that library of soil compositions, so that the Olympus system can autonomously diagnose its material and adapt its behavior without human intervention. This is the part of the story that tends to get lost in the excitement about glass domes and laser printers. The fundamental science, the mineralogy, the materials testing, the thermal analysis, the mechanical strength evaluations, is being done methodically and rigorously. Right now, it is being done at universities, at NASA centers, and at private companies working under federal contracts. The progress is real, the timelines are credible, and the engineering challenges, while significant, are being addressed one by one. The story of the glass moon is ultimately a story about human problem solving at its most ambitious and most disciplined simultaneously. The challenge is as extreme as anything our species has ever attempted. The environment is lethal. The distances are beyond ordinary comprehension. The resources available are strange, abrasive, and unlike anything engineers have ever used on Earth. And yet the response has been methodical, patient, and rigorously scientific, melting dust, testing ceramics, building simulated chambers, writing academic papers, earning one result at a time. Every major leap in human history started exactly the same way, with someone looking at a material the world had always dismissed as worthless, and asking one simple question: what could this become? On the moon, that material is dust. And the answer, it turns out, is everything.